There's something strange in our universe, that which refuses to be seen. 95% of it is hidden, dark, unexplained. No telescope has ever been able to truly chase it down. But one machine has been so radically engineered, it can scan the sky in a way fundamentally different from anything done before. It doesn't just take pictures, it films the entire universe in motion to reveal what laws of nature try to hide. This is the Vera Rubin Observatory, the machine that will film the living universe for 20 billion previously unknown galaxies and maybe tell us what it's really made of. The genius engineering of Vera Rubin Telescope might prove to be the ultimate weapon to reveal the invisible. Imagine watching the entire night sky unfold like a time-lapse movie, not over days, but over a decade. That's exactly what this observatory is about to deliver. Using a revolutionary telescope design, a groundbreaking data infrastructure, and the most powerful digital camera ever built, Rubin will capture the largest cinematic portrait of the cosmos in human history. To make this vision possible, engineers had to invent completely new systems and reimagine existing ones. At first glance, the observatory doesn't look like your typical telescope facility. And that's no accident. After rigorous testing, engineers chose the highest, most stable peak of the dome and setting the service building just slightly lower to the east. This precise layout offers some of the best astronomical seeing in the entire region. Even the tiered design of the service building isn't just for looks. Those layers help channel wind around the structure, reducing air disturbance inside the dome where image clarity is everything. And since this region of Chile is no stranger to earthquakes, the observatory has been built with seismic resilience in mind. From the cut section on right, you can see that the dome and service building are slightly separated, allowing each to move independently during a quake. On the left, it seems the telescope is moving, but actually it's the dome. We have had telescopes that zoom in deep and scan wide, but never both. Never this fast and this deep. Rubin literally changes that. Capturing a sky so vast in every frame makes even James Webb look narrow vision. The focal plane of this telescope is so large, its field of view can image 45 full moons. That's what it does with every single image, covering nearly 10 square degrees of sky at once. For comparison, the James Webb Telescope's near-infrared camera captures less than 0.05 square degrees, just a tiny fraction of a full moon's width. It combines this vast field of view, moving speed, and extraordinary light collecting power, allowing it to detect incredibly faint, distant, or fast-moving objects in a single snapshot. It's like switching from a flashlight to a floodlight and aiming it across time itself. But how do you build a telescope that can stare across time and do it 1,000 times a night? At the heart of this telescope lies one of the most interesting engineering experiments in astronomy, a 2-in-1 mirror. It's the first telescope in history to combine the primary and tertiary mirrors in a single surface, each with a different curvature. It's a single massive disc of low-expansion borosilicate glass coated in an ultra-thin 120 nanometers layer of pure silver and protective layer of silicon nitride. So, when light from distant space hits the outer 8.4 meter diameter primary mirror, it's reflected upward to a 3.4 meter secondary mirror. And from there, the light bounces back to the inner 5 meter section of that same glass, the tertiary mirror, and finally shoots up to the camera. But why not just have 3 separate mirrors? This simple question actually solved one of the biggest problems of astronomy. Early designs had 3 mirrors, with light having to travel a longer distance to hit the tertiary mirror. This would have made the telescope a lot longer. By placing the first and third mirrors on a single slab, engineers made the entire telescope shorter and more agile. This simple change is one of the secrets behind Rubin's lightning-fast repositioning, snapping up to 1,000 images in a single night. And yes, a shorter telescope vibrates less, meaning razor-sharp and clear images. While it might look as a single piece of glass, the mirror isn't a solid chunk. Its back is sculpted into a honeycomb structure, making it lighter, stronger, and easier to cool evenly. Technicians layered ultra-pure glass over a honeycomb mold and then spun the entire assembly in a searing hot oven to melt it into a perfectly curved parabola. After cooling for months, it was meticulously ground and polished. A mirror so precise, even a hair-width flaw would ruin its focus. Rubin is also unique in that it utilizes the largest and the most powerful digital camera ever built. Weighing a staggering 2,800 kilograms, the camera isn't just the largest, it's a technological masterpiece. Inside the camera, the sensor that takes the image is 2 feet by 2 feet. It's made of 189 small pieces that, when combined, results in a mind-blowing resolution of 3.2 gigapixels. This enables it to capture images so detailed it would take 400 Ultra HD TVs to display just one of them. And it's not seeing in just one color. Equipped with 6 massive color filters that span the spectrum from near ultraviolet to near infrared. 5 of these filters can be loaded at once into a motorized carousel inside the camera, ready to be swapped by a robotic system called the auto changer. Each of these filters is a precision-cut 30-inch glass disc with a special coating that allows its designated colors of light to pass through while reflecting the rest. And the entire switching process from one filter to the other takes less than 2 minutes. That's a level of automation and speed unheard of in instruments this size. After bouncing through the mirrors, the light gets focused by the camera's 3 lenses onto the image sensors. The camera's electronics convert the light into data, which is then transferred off the mountain and sent to different locations around the world to be processed and readied for science. But a camera of this scale needs more than just lenses and filters. Inside Rubin's camera, even the tiniest temperature shift could spell disaster. This happens because a slight thermal expansion or contraction could warp the focal plane, leading to blurred or distorted images. To maintain razor-sharp clarity, the camera is equipped with not one, but 2 advanced cooling systems. Here is the cryostat assembly inside the camera just behind the focal plane. The first cooling system inside the assembly chills the analog to digital electronics using a 2-stage cascade refrigeration system, wherein, instead of 1, 2 cascade cycles cool the target down to minus 40 degrees Celsius. But the real magic happens deep inside the cryostat, where the camera's ultra-sensitive eyes, the charge-coupled devices, are cooled to a bone-chilling minus 130 degrees Celsius. This extreme cooling is achieved using an advanced auto-cascade refrigeration system. A typical auto-cascade system has a refrigerant mixture that is first compressed together, then enters a phase separator. Inside, one component condenses into a liquid while the other continues as a gas. The high-temperature refrigerant, shown in yellow, then evaporates to cool a shared heat exchanger. This exchanger, in turn, condenses the lower-temperature refrigerant, in blue, which passes through its own evaporator. This cools the CCDs. Once the process completes, the gas mixture, shown in orange, returns to the compressor and the cycle begins again. A self-sustaining system to deliver ultra-low temperatures. Now imagine if instead of 2, you have 10 components of refrigerant, each chosen to optimize the cooling process and remove any cold spots. This requires extremely precise systems engineering in action. And that's what exactly happening inside this camera, preventing even the slightest distortion in image clarity. The Rubin Observatory's heart may be its massive mirrors and ultra-sensitive camera, but without a body to hold them steady, they are powerless. Enter the telescope mount, a giant steel skeleton engineered to cradle over 300 tons of scientific hardware. This mount isn't just strong, it's fast. In just 5 seconds, it can shift, stabilize, and refocus on the next slice of the sky. But how do you make 350-ton structure move like that? The secret lies in its compact arrangement of mirrors and camera that keeps the majority of mass centralized. Banks of massive capacitors placed beneath the mount power this motion, delivering over a megawatt of instant electrical punch to accelerate or halt the telescope in seconds. And just like a regenerative braking system charging a car battery, it feeds energy back into the capacitors every time it slows down. Unless we look at its base, it's difficult to make out that this 300 tons giant doesn't roll but floats. A thin, high-pressure film of hydraulic oil, just 70 microns thick, about the width of a human hair, lifts the entire mount off its base. This bearing system creates a near-frictionless glide, so effortless that you could actually rotate this mountain of machinery with just few pair of hands. But Rubin isn't just watching the universe, it's talking back. It detects anything that's moved, flickered, or exploded in the night sky using a technique called difference imaging that subtracts the template image pixel by pixel from the new images it takes, leaving only the changes. This way, it processes the images in near real time and sends out worldwide public alerts within 60 seconds. And this isn't just once in a while. It will generate up to 10 million alerts every single night. And over its 10-year mission, 60 petabytes of raw image data, making it the most massive public archive of astronomical data ever created. To handle this torrent of information, the observatory relies on a global digital nervous system. Fiber optic cables carry raw data from the Chilean mountain top across continent to the SLAC National Accelerator Lab in California, from where the data is distributed to science centers across the globe. So what does all this mean? Why spend decades crafting micron precision mirrors and lightning-fast systems? Because we are chasing the biggest questions in existence. What is a universe made of? What's lurking in the shadows between galaxies? How mass is distributed across the cosmos by measuring distortion of light to the utmost precision due to gravitational lensing as the light travels past the galaxies to uncover the unseen asteroids in our solar system, and much more. And it's happening right now, in silence, atop a remote mountain. This observatory isn't just watching the night sky, it's watching the universe become history in real time.